Okay, this is the video on acid-base titrations. We're going to go through questions on this because that's what you're going to get. And let's get on with it. So we go here, we're going to use these equations. So you need to get used to these equations. And we've used them in other times already. So I'm going to go straight forward and describe how to produce 250 centimeters cubed of 2.5 moles per decimeter cubed NaOH. So this is making a standard solution. So this is a common question, and in your second year of A-levels can be quite a large one, okay? But this is for your first year. So we're going to go through just how to do the calculation. So first of all, to change, remember, decimeters to centimeters cubed we might need to do, centimeters cubed to decimeter cubed we might need to do. So for decimeters to centimeters cubed times 1,000, for centimeters to decimeters it is divide by 1,000. So keep those at the bottom there. We're going to use a volumetric flask to do this, and we normally do this, and that gets you a mark. Okay, so that's really important. So let's start then, shall we? Move that to the side, and let's go through the questions. So we have got the answer here. So first of all, use number of mole, volume, times concentration. Okay, so the concentration we want is 2.5. You can see over there. The volume we want is 250. Now that's converted to decimeters already, so this is in decimeters. Okay, because 250 centimeters cubed is 0.25 decimeters. So that times by 2.5 gives you 0.625 moles. That's the moles of the NaOH you need to put in to the 250 centimeters cubed. And then what you do is you take the number of moles, you times it by the molecular mass of the thing that you're trying to make, the NaOH, and that gives you 25 grams. So to be able to make this standard solution, you put 25 grams of your NaOH into your 250 centimeters cubed of water. Next question. Okay, let's look at the marking points if you're making standard solutions. Okay, first of all, you're going to dissolve that 25 grams of the solid in distilled water, less than 250 centimeters cubed, and you're going to do that in a beaker. So these are the bigger questions you might get in your second year of A-levels. The first one was just the calculation. This is how do you actually make that standard solution? And these are ones that people get wrong all the time, and they're very standard. So you mix whatever you've decided to dissolve, 25 grams, into distilled water. It's got to be less than the volume you want to create. So you can say 100 centimeters cubed, for example, if you wanted, but it's got to be less. You'll transfer the solution to the volumetric flask. So you'll stir it around and you'll transfer it and ensure that all of the solution is washed out of the beaker. Now, what that means is you'll take this beaker, you'll pour it into the volumetric flask, and then you'll put a bit more water in, wash it around, and then put those and transfer those into the volumetric flask. The green bits are the bits you get marks for. Okay, so once you get them into the volumetric flask, okay, everything in, it should still be less than 250. So you then need to make the solution up to 250. And you go to the bottom of the meniscus, okay, you do it with distilled water. And again, all the green bits are the minimum you can say to get the answer to this question. And you invert the flask several times. Interesting fact, there was research done once to say how many times did you need to turn it upside down, invert it, to make it so the solution was completely uniform and throughout. And it was 23. Okay, so you might find people doing it 23 times within the lab. Okay, and that is how you make a standard solution if you're just doing the calculation, or you're doing the calculation and you're doing all the marking points on how you actually do it. So we're going to now look at how to do a calculation based upon this to do the concentration, and also look at this question down here, which is what is meant by concordant titers. So that's a quick answer and you have to remember it. So let's put it to the side and let's just tell you. So titers that agree within 0.1 centimeters cubed. So you have to do more than one titer, more than one titration, and the answers have to be within 0.1. And you only average the ones that are within 0.1 of each other. The rest are anomalies or outliers, and you don't include them in your average. So let's have a look now. We've got the same question, and we're going to look through and see how we calculate the concentration. So let's look at the question here. You've got 25 centimeters cubed of the barium hydroxide. Student titrates this solution by adding nitric acid from the burette. The equation is below, so you can see the balancing. Okay, you've got a 1:2 ratio here, so 1:2 ratio here. Okay, so that's really important. Student repeats it until concordant tides. Remember, we said that was within 0.1 centimetres cubed of each other, and the mean titer of that is of the 0.160 moles per decimetre cubed is 26.75. So we've got a titer of this acid which we've added, which means we need to find the concentration of the barium hydroxide because we don't know that. So we're going to find that out. So first of all, let's do the number of moles. So the number of moles, as we used in the previous one, is going to be the volume times the concentration, okay, or the concentration times the volume. Now what you see here is 0.160. So this is our 0.160, our concentration, and times by our volume. So we know our titer is this. Now to convert that, remember we said at the start of the film that the volume here has to be changed into decimeters within this, and do that by dividing by 1,000. And so we've divided by 1,000 and given that number right there. And that gives you your number of moles. Now, number of moles of barium hydroxide in 25 centimetres cubed. So we know that this is the number of moles of the HNO3. So this is the number of moles of HNO3, but it's titrated against barium hydroxide 25 centimetres cubed. Now, that means here's your ratio coming in, BaOH2 to HNO3, okay? Which means that the ratio is for every mole of HNO3 will get half as much of or use half as much of the barium hydroxide. So that means if we've got 2 moles of this, we'll have 1 of this. Or if we have 4.28 times 10 to the minus 3 divided by 2 will give us our number of moles of the barium hydroxide. So that's why we divide by 2. Last thing is the concentration. So the concentration is going to equal our number of moles of barium hydroxide, which we've calculated, okay? And we want to find out what it is in per decimeter. So concentration is going to be equal to, if you look at our equation here, we've got number of moles equals volume, concentration times volume. So that means to find out the concentration, we know the number of moles here, which is 2.41, okay, is the number of moles in 25 centimetres cubed. Now you can do multiple ways of doing this last bit, but I'm going to explain this because this is what you'll see in exam mark schemes, and often students don't understand what it means. So what we do is we know this is the number of moles in 25 centimetres cubed. So this is the number of moles in 25 centimetres cubed. I want to make that clear. This is our final answer, and this says moles per decimetre cubed. So moles per decimetre cubed. Now, this is in 25 centimetres cubed. How many 25s go into 1,000? Because 1 decimetre is 1,000. Well, you find that out by doing 1,000 divided by 25. That will tell you how many times 25 goes in, which is 40. Sometimes you'll even see it written in mark schemes that it says times by 40. And that makes no sense to people. What we're doing is we're just converting this from 25 centimetres cubed up to a whole decimetre cubed, which is 1,000 centimetres cubed. So that means 25 times 40, which is how many times 25 goes into 1,000. Okay, and that will give you your final one. There's another way of doing this, and you can do that by rearranging this equation as well. But this is the way that's shown in the mark schemes, which is why I've gone over it in this video, because sometimes it's very confusing. So we're still looking at the reaction that we did in the previous question, and this is a good time to introduce one of the indicators that you're going to use in your A-levels. Strong acids and strong bases use phenolphthalein, and we'll go into much more detail in the second year of A-levels about using methyl orange as well, and we'll also talk about phenolphthalein as well there in titration curves. But for now, let's just look at this colour change, because colour change is very confusing for a lot of people. So it's pink with the alkali in the conical flask. So remember, it's the alkali in the conical flask. Okay, the alkali in the conical flask, it will be pink. If it's acid in the conical flask, it will be colourless. Okay, so let's imagine we started with the alkali in the conical flask, okay, and we're adding the acid. That means our colour change will be pink to colourless. If we were going the other way around and we started in the conical flask with the acid and we added the alkali, it would go from colourless to pink. And they change those around as they do it in the exam, so make sure you read the question properly. So in this question, we're going to have to work out N. So what is N? If you're not sure, stop the video, read the question in full before I carry on. But if you look here, we've got an acid, glutaric, and I'll go across here. You can see there's an N here. This N says how many CH2s I've got. So we've got to work out what that value of N is. We dissolve this amount of glutaric acid. That straight away gives you a mass, which means at some point you can work out the molecular mass because you've got a mass. You just need to know the moles of the glutaric acid, then you can work out the molecular mass. Now that's in a 250 centimetre cube volumetric flask, and we take out 25. So there's a factor of 10 difference between here and here we're going to have to use at some point as well. The student titrates the solution with 0.24 NaOH in the burette. Okay, so it's adding the NaOH to the acid, uses phenolphthalein, tells you the changes, and then state the colour change observed at the end of the titration. Now, let's talk about that now. Colour change, remember you're adding alkali to the acid. So the acid is in the conical flask. So it's colourless in acid, phenolphthalein, and then you add the sodium hydroxide, so it will be colourless to pink. So colourless to pink in this example. So let's have a look at the data. So we've got some data here and we've got a trial. So first thing we're going to do is we need to calculate the titers by putting the numbers in and then minusing the smaller numbers away from the larger numbers. And if we got that, we have got these numbers here. Next thing is we've got a trial data and we've got 1, 2, 3, the trial. Now we do not use the trial data in any calculations whatsoever, and we do not use that because the trial is just there to estimate the titers, so roughly where it's going to be. And then we look at these values here and we take two of the values that are within 0.1 of each other, or 3 if they are. Now you can see 18.2 and 18.3 are within 0.1 of each other. Also notice that all of these have 2 decimal places, and you will lose a mark if you don't do them all to 2 decimal places. Really important, 2dp. Then, let's do the question. Why does the student carry out trial titration? Do you remember? Okay, it's to estimate the titer. Right, let's go on to the actual calculation part. So calculate the value of N in this acid, give your answer to the nearest whole number. So here is your average titer. So we've taken these 2 numbers here, so these 2 numbers right here, okay? And we've just averaged those, and I've got 18.25. And we omitted the anomaly, which is 18.05, and we didn't use the trial. So we do the number of moles of sodium hydroxide first because we have the concentration, which is 0.24, which we got from over here. So you can see it's in orange. Let's go down here. There it is. Okay, so there it is. Okay, and then this is the volume. This is the titer, but we turned it into decimeters. Okay, and then now we've got the moles of the sodium hydroxide. Now those moles of the sodium hydroxide, if I get down on one knee here, the moles of the sodium hydroxide, okay, will turn into the moles of the acid. So how do we do that? Look, we've got a ratio here of 2 to 1. So here we do is we divide it by 2, okay? So we divide it by 2. So we take this number, divide by 2. That gives us a number of moles of the acid. Now that's the number of moles of the acid in 25 centimeters cubed. But if I said, I'll get down again on here, you can see 25 came out of the 250. So there's a factor of 10 difference here. So we need to times this number by 10. That gives us the number of moles in 250 centimeters cubed. Now we've got the number of moles of the acid. We've got the mass of the acid over there, which is 2.891. And then we can work out the molecular mass. So here is our mass divided by our moles, because its molecular mass is the mass divided by the moles. So there's your moles here. Here's your mass. And we've got a molecular mass of 132. Because it's 132, what we can do is a quick calculation. We can take away all of the parts that aren't the CH2, so COOH and COOH. And we can take the mass of those away from 132. That leaves us with 42 left. If we divide 42 by 14, and hopefully you realise why we divide by 14. We divide by 14 because 14 is the mass of CH2. So if we divide by 14, we'll find out how many times 14 goes into 42, which is 3. Which means N is equal to 3. It's a very complicated question, which is very, very common if you do the AS examination, and if you don't, it will be more common in the full A-level paper, but worth less marks. Anyway, that's That's how you do it. So this is our citric acid that's neutralized by sodium hydroxide, as shown in the equation here. Notice the 3:1 ratio, and you're making sodium citrate here, but that doesn't matter. 3:1 ratio. Now, your citric acid is in a 250 centimetre cubed solution. So it's a 250 centimetres cubed solution. We took 25 centimetres cubed out and we titrated it against the sodium hydroxide. Let's put this to the side. Let's do the calculation. Now I'm going to put the numbers in. I'm not going to show you all the data because we're going to go through this one quite quickly because it's very similar to the one before. So we first of all do number of moles of sodium hydroxide. The actual volume of sodium hydroxide added was 27.35 centimetres cubed. So we converted that into decimetres and times it by the concentration of the sodium hydroxide, which was added, which was 0.8. We got a number of moles of sodium hydroxide. Then we wanted to know the number of moles of the acid in 25 centimetres cubed. And this goes back to the balanced equation, the 3:1 ratio. So 3:1 ratio, so we divide by 3, that will get our number of moles of the acid, which is 0.00729. Now we want to do it in 250. There's a factor here of times by 10. So times by 10, and there we have our number of moles of the citric acid. Now we want to know the mass of the citric acid in that 250 centimetres cubed. Now that is our number of moles times our molecular mass. Again, this is all rearranging moles equals mass divided by molecular mass. And we get 14. And this is where most people stop because they think they've got the right answer and they're missing out the final mark. Okay, so the final mark is what is the mass of citric acid in 1 lime? So we started with 2, we're going to 1. This is 2, we want to go to 1, so you need to divide by 2 to get 7 grams. Okay, and you've got 7 grams of citric acid in 1 lime. Next part of this question is changing the dilution and maintaining the titer. So they changed the dilution from 0.8 to 0.2. That is a factor of 4 difference. So if you're changing the concentration of the sodium hydroxide by 4, okay, then if you want the same titer, you have to make sure that the citric acid has been divided by 4. So what methods can you do to divide the amount of moles of citric acid by 4? Now, just to remind you, the original concentration was done, or the original solution was done in 250 centimetres cubed. Okay, right, so this is what you do. You take half a lime, because we start with 2 limes, and 1/4 of 2 limes is half a lime. Okay, the other thing is, we can make the solution up to 1 decimetre. It was 250. 250 times 4 is 1, which means that you will become 4 times more diluted. So half a lime would make it 4 times more diluted, or just make up to 1 decimetre. Also, dilution ratio. Just put in 4 times less. This will result in you putting in 4 times less citric acid or lime juice. So both would get you your marks. So our next question on titrations is how to work out what a metal is. What is the identity of a metal? So the metal is named as M. A student carries out an investigation to identify the group 1 metal, so it's telling you it's group 1. Okay, and that's why the formula is MOH, because M must be plus and the OH must be minus. And then they react 2.62 grams of the group 1 metal with water. That makes the alkali, MOH, and then that makes the solution up to 250 centimetre cubed with water. So we've got a dilution factor there, okay, because there's 25 and 250, so a dilution factor of times 10. The student titrates 25 centimetres cubed of this MOH with this sulfuric acid, and here's your equation below. Let's move this to the side. When we move to the side, you name the type of flask that students use to make up the 250 centimetres cubed solution. Is your first question. Well, that is a volumetric flask all day long. Beautiful one there. Okay, so hopefully that should be an easy question. So we're now going to calculate the amount of moles of MOH in 25 centimetres cubed solution to determine the identity of the group 1 metal. So we've got a titer, we're given a titer here, okay, and we know we're titrating from reading this, we're titrating the sulfuric acid against the MOH. So titrating against the MOH. Those two together, concentration and a volume, are going to create a number of moles of the H2SO4. We then need to convert it into the number of moles of MOH, and you can see MOH is a 2:1 ratio, so we convert it by timesing it by 2, and we get our moles of the MOH. It gets a bit tricky as we go on here, so make sure you're paying attention. So next thing, we apply the dilution factor, because in the question we take 25 out of 250, so we need to times it by 10. That gives us our number of moles of MOH in the 250. And last thing, and this is really confusing, okay? Really confusing, right? Now, the metal at the start is 2.62. So the metal at the start is 2.62. It's the metal, it's not MOH. So if the metal is 2.62, you divide it by the number of moles. Now, the number of moles is the same as the MOH. Now, why might you ask that? Why is the number of moles the same as the MOH? Well, there's a 1-to-1 ratio between the whole of the MOH and the M. So in 1 mole of MOH, there is 1 mole of M, which means if I have, for example, 2 moles of MOH, I have 2 moles of M. So it's the same number of moles, which means basically that number, even though it's the moles of MOH, it's the number of moles of the M as well. So therefore, 2.62 divided by that gives you the atomic mass, which is 39.1, which you can then look on the periodic table and find out is potassium. So this is our final question on this video, working out the percentage composition by mass. So if we look here, we have got a descaler, which is CH3COOH, which then reacts with the sodium carbonate. Okay, so when that reacts with the sodium carbonate, okay, you will find out how much of the descaler is CH3COOH, because we're given a mass of the original descaler, which is 6.5. That means some of that 6.5 is this acid. We need to find out how much. So we take the descaler, we dissolve it into the 250 centimeters cubed volumetric flask, and we make it up to the mark. Then we pipette 25 out of the 250. That's a times 10 dilution again, like we've done before. Okay, and in the conical flask, we add a few drops of the indicator. We titrate it with sodium carbonate that's in the burette, and we've got a titer of 24.2. So we want to calculate this percentage composition of the CH3 in the descaler. So we need to find out the mass of the CH3COOH to divide by its original mass, which is 6.5. Okay, so we're going to start off with the first one. The first one is you always work out what you can work out. And I'm given a titer, which is 24.2. I'm given a concentration, which is 0.2, which means I can work out the moles of the sodium carbonate. And I've just times those two numbers together. Okay, remember the titer's got to be converted to decimeters. From that point, I can use my ratio, and I can see the ratio here is 2 of those to 1 of the carbonates. Okay, we've got the carbonates, so we need to times by 2 to get the acid. So we times by 2 to get the acid. Remember, that is in 25 centimeters cubed because that's what you pipetted and you titrated against. Now I need to find out what's in the 250, so there's a conversion to and a calculation of times by 10. Okay, and we've got our value here. Then from that point, we can calculate a mass because we've got the moles. Okay, and we know the molecular mass of this is 60. If you work it out, stop the video, work it out yourself, but it's 60. Okay, so if we do moles times molecular mass, that will give us our mass. Okay, and here we have it. Our moles times our molecular mass gets us our mass, which is 5.808. The original mass was 6.5, so if you want a percentage, all you do is divide what you got by the original and times by 100, and you get 89.4%. And that is the end of all of the exam style questions that you can do to do with titration. We've looked at all of them, and these are all of them, so hopefully you feel well prepared.